am going to get started on this intro to proofs. I'm going to get started with this equation here. And remember the car activity that we did, and we'll refer to that a couple of times. So in this equation, this is an algebraic equation that you should already know how to do. What is the first thing you would do to solve for x here? Yeah.
Distribute the negative 2 to everything inside the parentheses.
Okay, good. So this would become negative x minus 18, then what?
Sorry, negative 18 plus 16x.
Equals 12. And our reason is just what he said, distributive property. So usually when we make you, solve an algebraic equation, we're not saying, well, give me a reason for every step. But we're going to do that here because it's going to kind of lead us to the idea of what a proof is. Yeah, Emmy. Okay? Good. Good. So you're going to combine like terms, and what's the result going to be? Good. Combine like terms. So our reason there is this combining like terms that we've learned about. All right, what is the next step you'd have to do here? Sam. By doing what? Good. Add 18 to both sides. It's going to cancel on the left and leave us with 15x equals 30. So our reason that 15x equals 30 is because we added 18 to both sides. We're going to call that the addition property of equality. Addition property of equality. All right, last step. What are we going to do now? Ewan? Divide by 15 on both sides. Good. And we get x equals 2 because division. And again, it's the division property of equality. Sometimes I abbreviate that as POE, property of equality. So, nothing was new there. You knew how to do that. Yeah, Emma, question? A proof, in general, is a convincing argument that uses deductive reasoning. That's a very vague, short definition of a proof. And there's a whole lot more to proofs than that, because we have two basic types of proofs that we're going to be doing. One is called a two-column proof. One is called a flowchart proof. There are other proofs. There are paragraph proofs and coordinate proofs, and there's lots of different types of proofs. Right now, we're going to start with two-column and flowchart. But in all types of proofs, you're basically following a sequence of logical steps, and you're justifying every step until you get from whatever given information they gave you to a final conclusion that they wanted you to prove. So it's going to take these steps all the way down. Okay? Question? So what we did up here is very much like a two-column proof. You're going to see in a minute what we're doing. Okay, so basically we start with algebraic type logical reasoning because you guys already know that. And then we're going to kind of segue into geometric proofs. Both have the logical reasoning. In algebraic proofs, when we're justifying every step, there's a bunch of choices that we have when we're justifying the reasons. Distributive property was one of them. We already, talked about that up here when we did our problem, right? The second step was distributive property. when they like define distributive property, they don't use numbers, they're going to use variables so that it pertains to all numbers, right? No matter what A, B, and C are here, distributive property works. And so it says A parentheses B plus C would equal AB plus AC, right? It's just how they do it in mathematical, chapters of books. Everywhere you look, if you look up the distributive property, they're going to have some sort of a definition there that has variables as the explanation. So the difference here, AB minus AC. So it's just saying that they're still equal. Combining like terms, 2x plus 3x equals 5x. This was an example that I gave. Basically, you're simplifying expressions by adding or subtracting terms that have the exact same variables. On the next page, there's a whole box of more, algebraic properties. The first four are basically the inverse operation properties, because if you have an algebraic equation where they add 10, we know we have to subtract 10, because that's the inverse operation, right? They divide by 2, you're going to multiply by 2. So all these are properties of equality, because if you have an equation, this equal sign says the left side is exactly equal to the right side. So what the addition property of equality says is that you can add the same exact thing to both sides, and it's still an equation. It still says that the two sides are equal. The left side is equal to the right side. We started with A equals B. Add the same thing to both sides. Subtraction property of equality. Subtract the same thing from both sides. Multiplication, we multiply. Division, we divide. The same exact thing on both sides. You guys are used to those. You might not have written it that way before, but you've used them a lot. Okay, substitution property. Also a property of equality. All of these properties of equality are used in equations. Equality, equal signs, right? Equations. So the substitution property is no different. It says if A equals B, then B can replace A in any expression. So if you think about the word substitute, right? Maybe you're making a recipe and there's a substitution because, somebody's allergic to gluten or something. So you substitute the flour for gluten-free flour or whatever, right? You replace an ingredient with something else. When I'm absent, a teacher comes in and replaces me. It's a substitute teacher, right? Substitution. Mathematically, though, they're exactly equal to each other. So if A is exactly equal to B, wherever there's an A, you can put a B, right? I like to do this. It's like a quick change. If they're exactly the same, you could throw one out and replace it with the other one, and it's the same idea, right? Same difference. Not going to change your equation. Quick change. Okay? So, a couple of things are really important about substitution. I hope that you guys treat these notes as like your textbook, because I'm not having you go look in the textbook that often, but I put a lot of things in these notes. So you should refer back to them. Let them help you, when you're looking something up, how to do something or something that you need to remember or study, you should be looking back at these notes. And these two things are going to be something that we're going to kind of go back to and keep reiterating. The first thing says substitution property can only be used in equations. You can't substitute into like a sentence. You can't say like angle A and angle B are vertical angles, and then have a statement that says, well, angle B equals angle C. So then take the sentence and say angle A and angle C are vertical angles. You can't do that. You can't take B out and put C in because you know B is equal to C and replace it in a sentence. It does not work. It only works in equations, okay? So keep that in mind. I'm going to keep saying it. This yep.
Right. So what's the time when gotta go.
All right. So this second thing that I have sort of triple starred is something we're going to have to come back to. It's not going to make much sense until we get a little deeper into our explanation of proofs. All right, a couple of properties that are not really algebraic properties, mostly used in geometry properties, are the reflexive property and the transitive property. Both are properties of equality, so again, used with equations. Reflexive property is just mind-blowing.
No.
You ready for it?
Yeah.
It says A equals, yeah, I know, right? So clearly that's not that, the only thing confusing about that is why do we have to make it a property, right? Everybody knows 2 equals 2, 3 equals 3, A equals A, right? But I promise you in geometry there will be a time when we're going to use this with actual, diagrams, and it's going to be a useful property, reflexive property. Transitive property is a property of equality. Think of transitive as like transition. One thing leads to another thing, leads to another thing, leads to another thing. So my example I like to use for transitive property, what if I told you I am the same height as my sister, and my sister's the same height as my mother? What could you conclude?
You're the same height as mom.
I'm the same height as my mom, right? So, well, I already said that. That's not a conclusion. That was one of the statements. So that actually brings up a good question. At the top of this page, bless you, I was going to do this next, but I'll do it now. I want you to write the word conditional. A conditional is an if-then statement. Well, the hypothesis is really just the if part. If something is true, then you can make a conclusion about it. So you may have gotten a different definition in science class or whatever, but an if-then statement is called a conditional. Think about if you asked your parents, can I go to the movies Friday night? And they might say, well, you can go on one condition. Right? No, boy, now there's a condition, right? It's a conditional. If you clean your room, then you can go to the movies. It's conditional. This has to happen first for the conclusion to happen. Yeah. Yeah. So, if you'll notice, most of our properties are in if-then form. Most of our theorems and postulates are in if-then form, right? If two angles are vertical angles, then they are congruent. If two angles are linear pair, then they are supplementary, right? We learned these things mostly in conditional form. If the first thing's true, then you make the conclusion. So with the transitive property, if we know A equals B, and we also know that B equals C, then we can conclude that A equals C. Right? So you wouldn't say, well, then I can conclude that A equals B. That was already given to us. That's part of the if. Now, just so you know, this is not limited to just three things. If A equals B, and B equals C, and C equals D, and D equals E, then what could we conclude? Then A equals E would be a final conclusion we could make, right? You could. Well, it wouldn't be a final conclusion. It would be a conclusion you could make from here, right? So, but Dylan's right. Once you have all of those givens, they're kind of all in the same equality pot, right? I mean, you could say anything's equal to anything. You have their statements, so you wouldn't want to repeat those, but you could say A equals D, B equals D, C equals A, E equals C. Doesn't matter. Any of those are all going to be equal to each other. Right? So, and that would all be by the transitive property. All right, so we've got these two-column proofs and these flowchart proofs that we're going to talk about. Have you heard of a flowchart before, like in general? Yeah. Flowcharts. Sometimes people use flowcharts to kind of show a progression or a summary of a unit or, you know, something like that. Two-column proofs look like this. There's always a given statement and a prove statement. This tells you what your first step is going to be and what your last step is going to be. So pretty much it tells you what you're trying to get to. But you have to break down all of the logical steps to get there. Now, if you notice, this is the exact problem we did on the first page. It's exactly it right here, right? Same exact thing. Notice the formality of the proof, though. Left-hand side, we label it statements. Right-hand column, we label it reasons. We have to make this grid. We have to number everything. We don't necessarily show all the steps of like adding 18. That's usually not shown. All you show is the result. So to relate it to the car thing we did, right, you're going to just change one thing. Change one thing. Every single one of these can be considered an if then. If 1 is true, then 2 is true. Why? Because of the distributive property of equality. Then I could change this and move it to here. If 2 is true, then 3 is true. Why? Well, if this is true, then 15x minus 18 equals 12 is true because we combine like terms. And then I can move this down again. If that's true, then this is true. Why? Because we added to both sides. Addition property. If this is true, then that's true by the division. Right? So this is the logical steps. A flowchart proof looks like this. Right? We've got, instead of two columns, we've got boxes and the reasons written underneath. So our given statement is in a box. Underneath that, we put our reason is given. Again, I could move this if-then from box to box. If that box is true, then the following box is true, etc. Now, this is a very boring flow chart proof.
Yeah.
Because it's just a box and then one arrow, and then a box and then one arrow. And then that's algebraic proofs are going to be like that. So let's get to one that's a little more exciting, like a geometry proofs. So this whole page is basically for your reference. Go back to these and look them over if you're ever stuck on how to write a proof, etc. That's all for your reference. So let's turn to this next page. We've already learned the vertical angles theorem. It says, if two angles are vertical angles, then they are congruent. By the way, this is the symbol for congruent. You guys seen that before? Okay, that means congruent. So So every time you see that, you can read it as is congruent to. All right, it's like an equal sign with a squiggle. All right, so if two angles are vertical angles, then they are congruent. Well, what do we know about what congruent means? If two angles are congruent, then their measures are equal. We can't say that objects are equal. You can't say an angle equals an angle. You can say the measure of that angle equals the measure of the other angle. But you can't say the object itself is equal. I can't say I am equal to my sister. That doesn't make sense. You could say my height is equal to her height. You could say my weight is equal to her weight. You could say my age is equal to her age. Anything that's numerical, you could say are equal. But things cannot be equal, right?
Orange can't be equal to that.
Right. Well, actually, an orange can't even be equal to another orange. Maybe the size could be equal to the other orange's size. The weight could be equal to the other orange's weight. But they're not exactly equal because they're separate things. But things can be congruent. So that's the word we use when we're talking about things, objects. All right, so by definition of congruent, this is going to be a reason that we use in our proofs when we're turning things that are congruent into saying they're equal, or vice versa. Two things are equal, we can say they're congruent. Two things are congruent, we can say they're equal. Both by the definition of congruent. Okay. I'm going to kind of go back to these. I think after we do a few ourselves, we can go back to that. Let's try a few if-then statements, okay? Our job is to give the reason for each of these if-thens. If angle 3 and angle 4 form a linear pair, then angle 3 and angle 4 are supplementary. What would be the reason that we know that? Yeah, Melanie. Exactly. It was that postulate that told us that if two angles form a linear pair, then they are supplementary. So our reason there is linear pair postulate. So when we write a geometric proof, that might be a reason. Okay, angle 5 and angle 6 are complementary. Actually, let me write this right here now. Reasons. Yep. Reasons can be postulates, theorems, properties, or definitions, or given. But for the most part, these are the most common things that are going to be your reasons in proofs. So try to think about postulates we've learned, theorems we've learned, properties we've learned, and definitions that you know. So if angle 5 and angle 6 are complementary, then we can say the measure of angle 5 plus the measure of angle 6 equals 90. What would be the reason that we know that? Aaron? Okay, so angle addition postulate is actually only in the case where you have a diagram with angles that are adjacent to each other and you're saying this little one plus that little one equals the entire thing. This just says they're complementary. You might have angle 5 on your paper and I might have angle 6 on my paper. They're not necessarily going to be an angle addition postulate. So what might be the reason here? Yeah. Good. Definition of complementary. If I say 5 and 6 are complementary and you say, oh, that means they add up to 90, I say you know that because you know the definition of complementary. You know what that word means. If angle 7 is a right angle, what reason would you have to conclude that the measure of angle 7 is 90 degrees. Yep. Definition of a right angle. Okay, now given this diagram, what would allow us to say that the measure of angle 8 plus the measure of angle 9 equals the measure of angle ABC? What would allow us to say that? Chelsea? Good. That one is the angle addition postulate, because we actually have the diagram to see that they're adjacent to each other. Make sense? Okay, when we get into writing geometric proofs, you're going to see that these are some common combinations of statements and reasons. Let me use like the vertical angles theorem as an example. You look at a diagram and you can say 1 and 3 are vertical angles just by looking at the diagram. If you make that statement, it's because you know what vertical angles are. It's the definition of vertical angles. I put optional here because it's not a step that I require you to do. If you're looking at a diagram and you're concluding, oh, look at that, I'm looking at a pair of vertical angles, it's a good statement to make. It's a logical statement to make. It's not one that I require. I let you go straight to this step if you want to. So you're looking at the diagram and you know you're looking at vertical angles, and you can say, oh, angle 1 is congruent to angle 3. How do I know this? Because of the vertical angles theorem. If you just have that step and not the first step, I know that you know we're dealing with vertical angles, right? Then going from that step to the next step. So if angle 1 and angle 3 are vertical angles, are congruent, then I can say the measures are equal. This is where I was talking about the definition of congruence. Going from a statement where you're saying two things are congruent to then saying their measures are equal is a definition of congruence. Notice the difference in notation. With congruence, there's no little m's, because those little m's mean measure of. Those little m's turn this into a numerical thing, right? Here's an angle. Once I measure it with a protractor and I figure out that it's 82 degrees, then the measure of the angle, I have that little m, right? And it's numerical, and that's what we need in our equations. All right, let's get to an actual proof. I'm looking at the clock, and I want to do this one. You should know that two-column proofs are the most commonly taught, I would say, in United States geometry classes. Mostly two-column. That's how I learned it. That's how most people teach it. But I teach flowchart proofs because I think that they make more sense. I think that they show more understanding. I think that in the long run, and usually I have a few people who fight me on this in the first few go-arounds, maybe even the first unit of proofs. People fight me and they're like, I like two-column better. Like, okay, you can do two-column, go ahead. That's fine. There's no penalty. And then we get into the next chapter, and everybody's like, wait a minute. I'm going to switch to flowchart, because flowchart ends up making more sense. The reason. Okay, so let's do this one together. The measure of angle 1 equals x, and measure of angle 3 equals 56. These are our two given statements. In a flowchart proof, you are going to put each given in its own separate box. Now, in a two-column proof, you write it all in the first statement, usually. But here we're going to make sure each given gets its own special box. Underneath every box is where you put the reason. You don't have a second column where you're writing the reasons. You're putting the reasons right underneath the box. Okay. Now we listed our givens. What we want to do is label the diagram. Don't forget that this is something I've been stressing from the beginning. Take your given information and write it in the diagram. When you do that, you can visually see the relationship. What kind of angles are these two angles?
Vertical.
Okay, so clearly we're going to be making a statement about these as vertical angles. Bless you.
Bless you.
What you want to do here is make a general statement. No substituting yet. You're going to make a general statement using the vertical angles theorem. Now, what does the vertical angles theorem say?
The two vertical
Are congruent. So what's congruent to what here?
minus 3.
Angle 1 congruent to angle 3. That is the general statement we can make from this diagram using the vertical angles theorem. Notice that our proof has an equal sign. So we have this problem of, all right, my statement is a congruent statement. I got to get it to be an equal sign. So you kind of have to transition it using the definition of congruence. So you're going to say angle 1 is congruent to angle 3. Therefore, right, if that was our if, my then could be the measure of angle 1 equals the measure of angle 3. Again, notice the notation. The congruent sign turned into an equal sign. At the same time, we had to put the little m's there, because now we're in an equation. The measure of angle 1 equals the measure of angle 3. Reason? Definition of congruent. You could just write it like that. Yep. Well, no, you would never use the word congruent with a number. Yep, because you're just talking about geometrically in this diagram, angle 1 is congruent to angle 3. Therefore, the measure of angle 1 equals the measure of angle 3. Now the magic happens, right? Now we say, aha, if I have this equation here, don't write this, but if I have this equation, measure of angle 1 equals measure of angle 3, and I know that the measure of angle 1 equals x, then I can kick out that measure of angle 1 and replace it with x. Then I can measure of angle 3 equals 56. So I can kick out measure of angle 3 and replace it with 56. So what's the reason? Substitution. So the reason why, and like I said, you don't write this here. I was just trying to show the substitution clearly, right? The reason there's 3 arrows here is because... What? Substitution. Substitution. Thank you. And you don't want to abbreviate that just sub, because there's subtraction, there's substitution. You got to make sure you write those words out. Okay? So, substitution property here. The reason there's 3 arrows is because this conclusion, this box right here, we used all 3 of those statements. We used this equation as our skeleton, right? And then we kicked part of it out and replaced it with something from here, kicked part of it out and replaced it with something from here. So all 3 of these were used to make this last conclusion by substitution. And that is always going to be true with substitution. If you're using substitution, you should be able to point to the equation you used and everything that got substituted in, right? Sometimes it's more than 3 arrows. Sometimes it's less. Okay, again, just really quickly, look at this version of the same exact proof. All of our givens would be in the first statement. Two-column proofs usually list all your givens first. Make sure you're copying your givens exactly. Step 2 would be angle 1 is congruent to angle 3 by vertical angles theorem. Step 4 is just saying that their measures are equal by definition of congruent. And step 5 would be our final substitution. Now, this is a very basic proof. You may think two-column looks more palatable. I'm going to skip that. Let's go to number 7 on the last, or on the next page. Okay, here I don't give you the boxes, but I ask you to write it as a flowchart proof. So you have to make your own boxes. I don't recommend drawing boxes first. I recommend writing the statements first and then putting the box around the statement. Otherwise, you're making a box, then you're trying to squeeze in. So there are 3 givens here. That means we need 3 separate boxes. Don't write too big. Each given gets its own box. Underneath it, we write given. So those are the givens. We put them in their separate boxes. Next thing we have to do is remember to do what? Label the diagram. 14x minus 12 goes there. Hey, my thing's a little off. 4x plus 4 goes there. And the whole thing is 17x minus 1. Now, if this was on your last test, you would probably go straight to just writing the equation that you could solve, right? And this is where we have to stop and back it up a little bit. Why can I write that equation? Well, because I know some generalities about geometry first. So we're kind of backing it up and breaking down so that we have every single logical step explained. So over here, we're going to make a general statement about this diagram. Not using the x values or the x expressions, but a general statement. What could you say? You see that? Measure of angle 8 plus measure of angle 9 equals the measure of angle ABC. What is the reason? Angle addition postulate, right. So again, a general statement first. Are we ready to do substitution? Remember, substitution is with equations. Do we have an equation?
No, we can't.
We have an equation.
Oh, yeah.
There's an equal sign, right?
Oh, yeah, we need substitution.
So now we're ready for substitution. Good. So now we're going to take this equation here, and we're going to rewrite it with each of these things, replacing the measure of angle 8, the measure of angle 9, the measure of angle ABC. So our result is going to be 14x minus 12 plus 4x plus 4 equals 17x minus 1. And the reason is substitution. Now it gets kind of boring, because now we're just going to do the algebra. 18x minus 8 equals 17x minus 1. Yep, combine like terms. Now, you might do this in a different order than the person next to you. It's okay. What would you do next?
I would subtract.
Robbie, what do you think?
I would add 8.
Okay, so we can't do both of those things at once because one is adding and one is subtracting. So we could do this in 2 steps. Robbie, I heard you say, could we add negative 17 to both sides? You actually could if you wanna do that. If you wanna say addition property of equality, and you're gonna add 8 to both sides and subtract or add the negative 17x to both sides. You wanna do it all in one step. You could do that. I'm gonna break it down just because it's our first time doing this, and I'm gonna leave it as 2 steps. So adding 8 to both sides would make this a plus 7. And that's addition property of equality. And then I'm going to make it x equals 7 by subtraction property of equality. Am I done?
Yeah, I know you see, I proved it.
Look, what was I trying to prove?
That measure of angle ABC equals 180.
Yeah, it wasn't x equals 7. That wasn't my proof, so I'm not done here. Exactly, but you have to show it in the steps.
Oh.
So, measure of angle ABC is 17x minus 1, right? Measure of angle ABC equals 17x minus 1. We already have that here, right? So all we need to do is use that step and this step and write it as the measure of angle ABC equals 17 times 7 minus 1. Just showing that you're plugging it into that particular angle measure. You guys see okay? And now I do not want you to do this in more than one step. Even if it requires more than one algebraic step, at this point I do not want you to do anything but one arrow that says measure of angle ABC equals, what is it, 112? 118. That's all I want you to do, and the reason I want you to give is just simplify. Oh, sorry. That's substitution, right? Because you plugged in. Anytime you're plugging in, it's a substitution. Does that make sense? You'll get the hang of it. Okay, I'm going to pause there because we're running out of time. Substitution is when you plugged in the 7.